And then in words, you will describe the unknown. So description of unknown in words. You should never have a number there, because if we knew what number x was equal to, well, we wouldn't need to call it x, right? So that should never be a number. So you have a variable, and then you say in words what it represents using one of the unknowns in your problem. The next is to translate the problem into an equation or system of equations. We'll be doing systems tomorrow. You will be doing systems tomorrow. So today we're just doing single equations. Then we'll solve the equation or system, and then we're going to use a sentence to answer only the question asked. In step 4, there should be no math. In other words, there should not be an x, there should not be an equal sign, ... We're writing in English. Because when somebody asks you how many square feet your garden is, have any of you ever answered x equals 30 square feet? No? I do that all the time. So in step 4, you're answering the question as it was asked. So imagine somebody asked you whatever the question was in the problem. When you write your sentence in step 4, you want to think about saying out loud to them what the answer to their question is. So there shouldn't be an x, there shouldn't be an equals. When we use this algebraic process, the variable is just a tool we use to get to where we want to go. It's not actually part of our answer. We just come up with it so that we can write an equation, do the whole thing algebraically, and then we have to actually answer the question. So we're using English in that one, not math. Okay, so let's do our first one. So an 18-inch board is cut into 3 pieces that we're going to paint 3 different colors. The red piece is half the length of the blue piece, the yellow piece is 3/4 the length of the blue piece, and we want to find the length of each piece. Okay, there are 3 unknowns in this problem. What are they?
Yellow, all colors basically.
Yeah, so the length of each board. So I'm just going to list them first. Of yellow, length of blue, and length of red. Okay, Stefan, what do you want x to be? Yeah, so he said that he was going to have x represent the length of the blue piece. Is everybody cool with why we chose the blue piece instead of the yellow or the red piece?
Just easier.
Yeah, it's easier because of these 2 sentences. Notice that this sentence tells us how to get the red piece or the length of the red piece from the blue piece. And then this sentence tells us how to get the length of the yellow piece from the blue piece. So those sentences tell us everything we need to know, all in terms of the length of the blue piece. And so we decide we're going to have our variable represent the length of the blue piece, because if we knew that number, we'd be able to get anywhere we want to go from there. Does that make sense? So you're looking for sentences that give one of your unknowns in terms of the other to figure out which one your variable is. So x is the length of the blue piece. So then how would I represent the length of the yellow piece?
X plus x minus 1/2. It would be half. So
Half. How do we find half of something?
X half.
over 2.
Half.
Yeah.
Yeah, you can divide by 2 or multiply by 1/2. Those are equivalent. Very good. So 1/2 x. And then the length of the red piece, yes. Oh, I'm sorry. This is red. And then the length of the yellow piece?
3/4 x.
Very good. So now we've represented all of our unknowns algebraically. So I often think of this in terms of words, algebra, and numbers. So I started by listing all my unknowns in words, and then I represented every single one of those with an algebraic expression. And then at the end, we're going to have a number for each one of those lengths. So the next piece of information I'm going to use is that I started out with an 18-inch board. That means that the length of all three of these pieces has to add up to 18. So we've got the length of the yellow piece plus the length of the blue piece plus the length of the red piece, and those all have to add to 18. What should I do next?
Get rid of the action.
Yeah, we're going to get rid of those fractions. So my LCM is 4. I'm going to multiply all 4 of those terms by 4 over 1. So we've got 4 over 1 times 3/4 x plus 4 times x plus 4 times 1/2 x equals 4 times 18. So eventually you guys will be able to clear fractions in your head, and I'm perfectly happy for you to get to that point at whatever time you feel comfortable doing that. Sometimes you'll see equations that it just seems simple enough that you can do it in your head. So if you don't write that whole step out, that's okay with me, as long as you feel confident in doing the process in your head. I promise all of you will get to that point for some of these simpler ones, but it differs how long it takes. So those 4s will cancel, and we've got 3x plus 4x equals, so 4 divided by 2 is 2 times 1, whoa, thank you. 4 divided by 2 is 2 times 1 is 2, so 72. So we'll combine like terms on the left. 9x equals 72, and divide both sides by 9. So x equals 8. What did we just find?
The blue.
Yes, we found the length of the blue piece. I recommend, so this is a habit that I always encourage everybody to get into, and it's what I do when I solve application problems, is as soon as I solve an equation, I ask myself what I just found, like in terms of the original problem, because the more complex these get and the more different unknowns we have floating around, the harder it is to figure out what everything is and how to get everything you need. So it's sort of just like going back to the beginning and being like, okay, x was the length of the blue, so that means the length of the blue is 8 inches. So length of blue is 8 inches. Then the length of the yellow piece is 3/4 times 8. We can do that just like we did the calculation when we cleared fractions. So I've got 8 divided by 4, which is 2 times 3 is 6. So length of yellow is 6 inches, and then the length of the red piece is 1/2 times 8. So again, multiplying by 1/2 is just the same as dividing by 2, so that's going to give us 4. And always a good idea to check your work at the end. So we use that 3/4 x and 1/2 x to get the length of our yellow and our red. We did not use the fact that they all add up to 18 to get the length of the yellow or red, which means that checking to make sure they add up to 18 will tell us if we did it correctly. So we often talk about checking answers to equations, and when we check solutions to equations, we just plug them back into the equation, make sure they make them true, right? But with application problems, usually when people make errors, it's in writing the equation. And so if you write an equation and you make an error there and then you plug your solution back in, you're going to, I mean, as long as you solved it right, it's going to say that you found a solution to the equation you wrote, but it won't tell you if you wrote the right equation. So when I get to this point, I go all the way up to the top and be like, oh, wait, they have to all add up to 18? 8 plus 4 plus 6 is 18. That's how I know I got the right answer. Rather than using our equation, which could be flawed. Good? Any questions on this one? Okay, let's do another. Okay, we've got two consecutive integers. So I have two unknowns. In words, we're just going to call them the smaller and the larger integer. So smaller.
So how are you going to write the, like you said, write the answer in a sentence? So you're just going to put the yellow is, or red, you know, blue is 8 inches, the yellow is.
I'm going to write that. Yep. So smaller integer. Larger integer. And on these ones, there's nothing really that tells us which one should be x. Just as a rule, I always make the smaller number x, and then I can build onto it to get the larger number rather than having to do subtraction. So I always, with these consecutive integer problems, I always just make x the smaller number. So x equals the smaller number. And then we have to get an expression for our larger number. What I always look for in these problems is there's always like two pieces of information. One piece of information tells us how the two unknowns are related to each other. And then the other piece of information tells us how they're related to some other number. So this sentence right here relates my two unknowns to the number 24. It doesn't relate them to each other. I mean, secondhand, it relates them to each other because of the way they're related to 24. But because that 24 is in there, it's not a simple explanation of how the two are related to one another. We don't use the information about how they're related to the number 24 until we write our equation. When we're setting up this first step, the only thing we care about is how the numbers are related to each other. Just like on the first example, the number 18 didn't show up anywhere in our setup, right? All we used was how the lengths were related to one another. We didn't care how they added up. So, how are these two numbers related to each other?
The consecutive numbers or the 2/3 and 24 numbers?
My two numbers.
So
Which
x
are
and x plus 1.
Yeah, so my two unknowns are consecutive integers. So this right here is what's telling me their relationship to one another. What are consecutive integers?
A number followed by the next number.
Yeah, they're just, now I can't think of another word other than consecutive. It's one number after the other, right? It's just counting. 1, 2, 3, 4, 5, 6 are all consecutive integers, which means that consecutive integers always differ by 1. So if my first integer is x, then my second integer has to be x plus 1. If this said consecutive even integers, how many would they differ by? 2. 2, 4, 6, 8, 10, right? So my larger number would be x plus 2. If these were consecutive odd integers, how much would they differ by?
2.
Also 2, right? Which is a little tricky because 2 is not an odd number, but that's okay. Our numbers can differ by 2 and be odd, right? 3, 5, 7, 9, 11. They all differ by 2 as well, which means that when I have consecutive odd integers and consecutive even integers, the setup is exactly the same. The only thing that makes them even or odd is the number they end up adding up to. But we're not there on this one, so I'll get rid of it. So now we're ready to write an equation, and that's where we're going to use that second piece of information. If you find yourself having trouble translating those sentences, you can literally go through word by word and replace it with math. So half is 1/2. The smaller integer I said was x, right? So the smaller integer is x plus is addition. 2/3 is 2/3. And then the larger integer I said was x plus 1. The word is always translates to equals, unless it's followed by the word greater or less. But we're not going to do applications with inequalities, so we don't have to worry about it. And then 24. So I think one of the keys to being successful with application problems, no matter how complex they get, is taking it little bits at a time. So I often see people try to read the whole thing and then do the whole problem, which is kind of hard because then you have to use like your working memory to remember everything you read, as well as figuring out what you should do. It's fine to go piece by piece and write things down as you go. So when I build this equation, I don't read that whole sentence and then write the whole equation. I'm like, oh, 1/2 times the smaller integer. And I write 1/2 times the smaller integer. And then plus, right? So go piece by piece. So you don't have to use your working memory for like a ton of different things. So 1/2 x plus 2/3 times x plus 1. And notice I had to put those parentheses in. And the way I know when I need parentheses when I'm translating a sentence is if I have an expression like x plus 1 that represents a single value, so a length, an age, a number, then I'm going to group it with parentheses. So because this entire thing represents one number in my problem, I'm going to put parentheses around it. So that when I do anything with that number, I'm performing that operation on the entire number instead of just a piece of it. So equals 24. What should we do next?
I mean, it depends, but I would do the 2/3 times x plus 1.
So you want to distribute next? Sure. So 1/2 x plus 2/3 x plus 2/3 equals 24. Now what? Yeah, we're going to clear fractions, right? As soon as I see those fractions, I know that before I start moving things around, I need to get rid of them. So I'm going to multiply both sides by 6. So 6 over 1 times 1/2 x plus 6 over 1 times 2/3 x plus 6 over 1 times 2/3 equals 6 times 24. So 6 divided by 2 is 3. 6 divided by 3 times 2 is 4. And then this one's the same. Oh man, 6 times 24. 6 times 4 is 144. So we'll combine like terms on the left, which gives me 7x plus 4 equals 144. Subtract 4 from both sides. And divide both sides by 7. So x equals 20. What did I just find?
Smaller digit.
Yeah, we found the smaller number. So now we just have to add 1 to it to get the larger one. So the numbers are 20 and 21. There's absolutely no need for you to say the smaller integer is 20 and the larger integer is 21, because when you give somebody the numbers 20 and 21, I'm pretty sure they know which one's bigger, right? The reason we do it over here when we're setting it up is that I have to have some way of distinguishing the two unknowns from each other so that I can represent them separately. But once you get to the end, if somebody says, what are those two numbers? You don't usually answer like the bigger number is, right? You just give them the two numbers and they can use what they know to figure out which one's bigger. Good? This is fun, right? Okay, you guys try this one. When you do this, draw a picture and label it so that you correctly write an equation for the perimeter of this rectangle. Because our equations aren't always just going to be the two variables added together. And make sure you start with step 1. Ooh. And remember, in that first step, we always use words on one side and then variables on the other. So L and W don't mean anything to me if you don't tell me what they are, right? L and W are just variables. So if you write W equals X, you're defining a variable with another variable, and you've never related it back to the original. I mean, I know that we've always used L and W for length and width. I mean, why isn't L like... I'm trying to think of something else that starts with L. Loan payment. Why isn't L the loan payment? Starts with L. Right? I mean, like, in different settings, variables represent different things. So that first step, it's all about using words to represent what you have. And I know I sound really annoying because I'm going to say there's stuff like over and over and over again. And sometimes I wish you guys could like fast forward 6 months so you could see why I'm so annoying about it. But there are problems that you'll get to in college algebra and calculus, etc., where you literally have like 10 unknowns. And if you don't really clearly say what all of them are algebraically at the beginning, then when you start solving stuff, it's so confusing. Like, what the hell did I just find? Right? So that's why I harp on you so much to be really specific in that first step. It's really the most important step of the whole thing, because then you can keep coming back to it as you find different things. So this guy I'm going to call X. And then my length is 1 more than 2 times my width. And then perimeter of a rectangle is the sum of the sides, right? We have 4 sides here. So we've got a width plus a length plus my second width plus my second length.
Could you just put it in parentheses with 2 and 2?
Absolutely. And that's 26. So combined like terms, was that 4x? No, it's not, it's 6. 6x plus 2 equals 26. 6x plus, whoops, equals 24. So x equals 4. What did I just find?
Width.
What do I want to know?
The perimeter.
No. Length.
The length. Yeah.
The length. So if you said the width is 4 and the length is whatever, I wouldn't take points off. But I mean, technically, nobody cares what the width is because they didn't ask, right? If somebody's like, how old are you? You're not going to tell them your mother's age, your father's age, your sister's age, your cousin's age, right? You're going to tell them just your age. So always go back and see what the question actually is. So the length is 2 times 4 equals 9. And we are in meters. So always use that expression up top, that 1 plus 2x, to come up with your length. We can't just subtract 4 from 26, because remember the perimeter incorporated 2 lengths and 2 widths, right? So if we just subtracted 4 from 26, we'd be taking away 1 width. So that would tell us the total of all 3 of these sides would be 26 minus 4, right? Excellent. I'm going to skip that. Whoa. Yeah, of course. Anytime.
So I ended up writing a different formula, but I got the same answer.
Did you write 2 times x plus 2 times 1 plus 2x?
Yes.
Yes, that's fine.
Okay.
I just wrote each of the lengths and widths out twice, rather than multiplying 1 length by 2 and 1 width by 2, which is equivalent.
Is that going to be the better way to do it, or?
No, there's not a better way to do it. I find that some people start to get overwhelmed when they feel like they have to memorize too many formulas. And so I try not to do stuff like this in terms of like the formula for perimeter is 2L plus 2W. But if you know that, or you can deduce it from what you know about finding perimeter, that's totally fine with me. I just don't want to overwhelm everybody with a bunch of formulas.
Okay.
I'm going to skip number 4. And we will do number 5. Okay, so a parking lot charges $2.50 for the first hour and $2 for each additional hour, and I paid $20.50 total. I want to know how long I was parked. What are my unknowns?
Hours.
Yeah, the number of hours I was parked, right? And in this problem, there's just one unknown. So x equals total number of hours parked. So now we're going to write an equation. So I know that my total cost was $20.50. Then on the other side of the equation, we are going to write down how we got there. So what do I have to pay for? Yep, I've got to pay $2.50 no matter what. And we can assume that they charge us for the entire hour if we stay part of an hour. That way we don't have to worry about partial hours. So $2.50 for the first hour. And in addition to that, I have to pay what?
2x. Because you don't know how many hours.
Excellent. Now there's only one problem with this, which is that I paid double for the first hour. So if I parked for 5 hours, then using this formula, I would say I paid $2.50 for the first hour, and then I paid $2 for 5 hours, which means I paid for that first hour twice, right? Does that make sense? I don't want to pay for the first hour twice.
Do a minus 250.
Well, we can't take off the $2.50 because then we'd just say I was paying $2 for each hour. So what we're going to have to do, like, what should this number really be? How many hours do I actually pay $2 for? 4, right? So when I multiply by the number of hours, we want to think of that as multiplying by the number of hours after the first hour, which is just 1 less than the total number of hours. So these problems are fairly simple, like when we first look at them, because we're like, oh, we just add everything up. You just have to be really careful with problems that talk about like paying different amounts for different portions of the number you're plugging in. So you never want to pay twice. The alternative is to say that x equals the number of additional hours parked, in which case you could write that equation as 250 plus 2x, but then when you get to your sentence, you have to add that first hour back in. That makes sense? So either one of those is fine. Again, you just have to be super clear when you tell us what your variable represents. Okay, let's solve. So we've got 2050 plus, no, equals, my goodness. 250 plus 2x minus 2. And you can kind of see what we're talking about here is this is $2 times the total number of hours. And then this minus 2 is saying take off the $2 I paid for the first hour again, right? So that's 2050 equals 50 cents plus 2x. So 20 equals 2x and x equals 10. So I was parked for 10 hours. Questions? Mike, what's up?
I'll just try and make sense of it. So you only took $2 off each side with the 250?
Oh, I was just combining like terms there. So on the right side, I have 250 minus 2.
Okay.
Good. Other questions? Okay. Moving right along. We're going to skip number 7 and number 6, incidentally, because I can't count.
Benefit to flipping, turning the equal sign the other way, doing the problem that way.
Like,
Yeah,
right.
where it's always, the total is always on the right.
No, I mean, there's not much of a benefit either way, so whatever you like better is fine. Okay, so we're going to move on to percent applications. So we solve percent applications algebraically. Again, this is something when we do this, the simple problems, it's like, oh my gosh, I did percent in 5th grade, and you just multiply and divide, right? So you can use arithmetic to do most of these simple problems, but again, we're talking a process here, not just an answer. So I want you to work on the process with the simple ones so that the process isn't the confusing part when you get to the more complex ones. So I always set up percent problems exactly the same way. So the basic percent equation is the equation we will use for every single one of these problems, which is kind of nice because you don't have to ask yourself, like you don't actually have to come up with an equation, you just have to come up with the pieces to plug into it. So the equation is A equals P times B. A is the amount, we call it. P is the percent. And B is the base. And depending on the problem, the base has one of two meanings. It's either the total or it's what you started with. So depending on if we're just taking a portion of a whole or if we're doing like a percent increase or decrease, like paying a tip on a dinner bill. If we're just talking about taking a portion of a whole, then the base is the total. And if we're talking about percent change, where we're like increasing something by a percentage or decreasing something by a percentage, then the base is always the value before the change. And the key to setting these up accurately is that the amount and the percent represent the same quantity. So these represent the same quantity. So what I mean by that is that if I have something like I paid $14. I want the word A in there. A $14 tip on a $70 meal. Which is a 20% tip. So in this sentence, the tip is represented in two ways. One is a percentage and one is a dollar amount. So this guy right here would be my amount. The amount represents that quantity in dollars, people, miles, whatever it is, whatever the units are. Whereas the percentage represents that same exact quantity as a portion of the whole, right? So a percentage is just a ratio, and then the amount is the actual value, so it's a set amount. Does that make sense? So when we set these up, we always assign words to the amount in the percent so that we can make sure they're representing the same thing. So like in this problem, I mean, I don't have an unknown here, but if I was going to have an unknown and set this up, I would write amount of tip and percent of tip. And because they're both the tip, I know I've set it up right because they represent the same quantity. So let's do a couple so we can see it. So amount, percent, and the base. In this case, what does my percent represent? I always look for percent first because it's the easiest one to find, right? Because it's the only one with a percent sign on it. What's my percent telling me?
The amount of freshmen that live on campus?
Yeah, so 90% is the portion of freshmen that live on campus, right? So this is percent is on campus. And then before I even worry about numbers or variables or anything like that, I'm going to take what's in those parentheses and literally copy it because my amount has to represent exactly the same thing. So if my percent is the percent of freshmen that are on campus, then my amount has to be the number of freshmen that are on campus. So my amount's actually counting people rather than a portion. So amount of on-campus freshmen. Stay. So now I'm going to worry about if I know these things, if I have values for them. So do I know the percent of on-campus freshmen?
90%.
Yep. Do I know the number of on-campus freshmen?
No. You know the base.
Right. I know that there are 1,200 freshmen total, right? I don't know, that 1,200 isn't the on-campus freshmen. So this one I don't know. And then my base is going to be the total freshmen. And so you're probably already noticing that in order for this setup to actually help us make sense of all of it, we have to be pretty specific in our labeling, right? Because if I was like percent freshman, that's not super helpful as far as actually telling me what my percentage represents, right? Because everybody we're talking about are freshmen here, right? So we have to be super specific that it's the percent that are on campus, right? Not just the percent freshmen. And my total freshmen are 1,200. And I know my base is a total rather than the beginning amount because nothing's changing here, right? Like I'm not taking the number of freshmen and reducing it or increasing it. I'm just talking about a specific portion of them. Does that make sense? Whereas like if I was going to say there's this many freshmen this year and this many freshmen next year, if I could see the future, then I'm actually talking about the number of freshmen changing. That would be a percent change situation where my base would represent the value before the change. So now we're going to write our equation. Again, your equation is always the same. Amount equals percent times base. So A equals P times B. So X equals 0.9 times 1,200. Which is like 108.
That's what I got.
Excellent. So 1,080 freshmen.
So I'm still getting used to this way.
Mm-hmm.
I did it a completely different way. I just want to know if I can continue to do it that way.
Depends on how you did it.
So I just did blank over 1,290 over 100.
No, who taught you that?
1,200 times 90 divided by 100. It takes forever, but that's how I figured it.
Do not use proportions. We tell them all. Do not.
But if I
It's like we have meetings for no reason. No, don't use proportions. So the reason we don't use proportions is because when we get into our percent increase and decrease, there's subtraction happening. And so it's not all just something divided by something equals something divided by something. So it's another one of those things where like proportions work great like for simpler problems, but then when we get into the more complex situations, they're just not as versatile as this equation. Any other questions? Okay, let's. Oh.
What are we not supposed to do then?
Oh, so you can solve percent problems by saying that a percentage is like a fraction of 100, like 90%. And so they're saying like if you take X divided by 1,200, that's equal to 90 divided by 100.
Yep.
And solving that, which is true. But again, proportions just aren't as versatile as this single equation. And they have fractions. Nobody likes fractions. And so for the more complex problems, solving with proportions isn't going to be as successful.
So how are we supposed to do it?
The way I did it.
But I mean,
That's why I did it that way.
I would just have a calculator, you know what I'm saying? How do you-
But we don't use calculators.
But that's what I'm saying, like, how do you do, like, 0.9 times 1,200?
Times 0.9. Let's see, 9 times 0 is 0, 9 times 0 is 0, 9 times 2 is 18, and then 9 times 1 plus 1 is 10. And then this tells me that there is 1 decimal point, so I want 1/10 of what I got, and so I move my decimal point 1 to the left.
It's better than dividing all that crap and then remembering.
I agree. I will always, especially on tests and stuff, I'll always give you ones where the calculations themselves are fairly simple. Like, I'm not trying to make everything super complicated. I just care about the setup mostly and using the process more than the calculation itself. And on your homework, like in my math lab, they may not necessarily give you nice numbers. So once you get to this point in my math lab, you can plug it into a calculator. I don't care, as long as you know how to do these simpler ones for the test. Because when I write the test, I make them nice. In my math lab, they generate random numbers, and so I can't guarantee they're quite as nice. But the idea is really in this setup. If you use a calculator in the very last step, I really don't care. Okay, let's do some more. Yeah, I'm going to skip that one. Number 10. So I want you guys to try the setup on this one. Again, we have an amount, a percent, and a base. Start by writing in words what the percent represents, and then copy those words for the amount. Okay, what does our percent represent?
Students that check their answers.
Yeah, students that check their answers. And I know it can get a little tedious here, like writing these big long sentences. What I really care about in this labeling portion is that you distinguish the students that check their answers from the total number of students in the class. So if you just wrote percent and then in parentheses you wrote checked, like I don't care, it doesn't have to be a long sentence. But if you wrote percent and then in parentheses you wrote students, that's not specific, right? That doesn't distinguish the students that represent the 40% from all of the students in the class, because everybody's a student. So it's not that you have to write a lot of words, you just have to write specific words. And that means that the amount also represents the students that checked. And then in this problem, the amount of students is not changing, right? We're just talking about a specific portion of them, which means that my base is a total. That's the thing I don't know. And so amount equals percent times base. 10 equals 0.4x. And we'll divide by 0.4 on both sides. As far as how to do that division, there's a few ways to do it. I think the easiest is to remember that if you multiply by 10, it moves the decimal point over one place. So if I don't want a decimal in my denominator, I can multiply this whole fraction by 10 over 10, which gives me 100 on the top and 4 on the bottom. And so 10 divided by 4/10 is equivalent to 100 divided by 4. That make sense? And that's just 25. So there are 25 students in the class. How are we doing? Okay, let's talk about percent change. So percent increase and decrease problems are exactly the same. I try to set it up so you guys could do the same thing every time, but you do have to recognize if you're in a situation where you're talking about a portion of the whole, or if you're in a situation where some value is changing to another value. Other than that, they're exactly the same. So our amount is going to be the amount of the increase or decrease. And so that means our percent is going to be the percent of the increase or decrease. And then base is going to be our value before the change. Or, and this is where labeling is important, you just have to ask yourself what they're actually giving you, because there's kind of two ways to set these guys up. The alternative to the amount in percent being how much it is changing by is that the amount in percent is what you're left with. So depending on what they give you in the problem, so if they give you a final or an initial amount, A can be the final value, value after change. Which means the percent is the percent that's left after the change. And the base is always the value before the change, no matter what. And so which one of these you're going to use really just comes down to reading the problem and basing everything off of what you're given. So we always want to work with what they give us, and instead of trying to manipulate what they give us to fit into some perfect little model. It's a lot easier to adjust our model slightly so we can work with what they give us than to try to like mess around with everything else. So it's probably easiest to see with examples. So let's do it. So I'm going to purchase a $75 coat in a state that charges 4% sales tax, which somebody in my last class told me is just non-existent. Apparently in Washington, it's 11%. That's crazy. Like the tax is more than a tenth. When I was a little girl in New York, I used to like walk around the block to like the candy store with $1, and like I'd find like a candy bar for 99 cents. But it did not cost 99 cents. You get to the checkout thing and it's like $1.07. Saddest moment of my life. Okay, we're going to purchase a $75 coat. So we've got amount, percent, base. Amount, percent.
Even though you could say that 4% is multiplied by 75.
Yeah, that tells us how much the tax is. Unfortunately, that doesn't help us with the problems where they don't tell us how much we started with, or how much it cost to begin with. Okay, so the percent in this case tells us what? Yeah, it's the sales tax, right? So, did those prematurely. So I have the percent tax, and my unknown is the total amount I'm going to pay. Except I don't get to make that A here. Why not?
Because it's total amount.
Right.
Base.
And I want my amount to be the tax. You could do it the other way. If you wanted to. This is really just a choice. If you're like, oh, my unknown is the total amount, with tax, then that means your percent has to be the percent including tax. You will get the same final result using both of these methods, but you have to be really clear with yourself about which you're doing. And that's why we use the words, because if you write percent tax and then you say the amount is the total amount I paid, then your percent and your base don't your percent and your amount don't represent the same thing. The percent represents the tax and the amount represents the total. I don't care which one you do. You just have to be consistent. You guys pick. What do you want? Left? Okay. So the percent is my tax. So that's going to be 4%. The amount is the amount of my tax, which I don't know. And then the base is the price. Remember, it's always before the change, so before tax. So X equals 0.04 times 75. $303. What did I just find?
You found the added on tax.
Yeah, I found just the tax, right? That doesn't answer my questions, right? I have to add that onto the $75. So always, again, when you get X equals a number, ask yourself what you found before you just go gung-ho into the next step. Yes?
So I know you like us to like show our work all the way out.
Mm-hmm.
But I hate doing the decimal. I like the fraction. I hate the decimal, so I just do 75 times 4, and then I just remember to move the decimal.
Yeah.
And that's
Absolutely.
You'll count it. Okay.
Yeah,
It's just easier for me.
at this point in your guys' math progression, when I talk about showing work, I basically mean showing the algebraic part.
Okay.
Like the calculations you do, I feel pretty good about you guys being able to do those on your own. Of course, if you show them over on the side, if you make a mistake, I can find it. But those calculations aren't really what I'm looking for as far as work. I'm more looking for the algebraic part. So what we just found was our tax. And so how much did my coat, is it a coat? Yes. How much did the coat cost total? $78. Good? Okay, here we go. This is the fun one. So I spent a total of $145 on dinner, including the tax. And I want to know what the price of the meal was not tax, tip. I want to know what the price of the meal was before the tip. So we've got amount, percent, base. So in this problem, I decided to set it up this way because I was working with what they gave me. They gave me that 4%, right? And I was like, oh, that's the tax. And so that's why I made my percent and amount represent just the tax, because I'm just working with what they give me. What did they give me here?
Well, they give you the total.
They give me the total, right? Is that the base?
No. That's the
No,
amount.
right.
Includes-
So the base is not 145 because that's not the value before the tip. It's the value after the tip. So I'm going to say my amount is the cost including the tip. Because that's what they give me. So my percent has to represent what?
Percent of
It's the same thing.
The same exact thing. Just copy. The percent and the... So the equation A equals P times B assumes that the percent and the amount represent the same quantity. So like once we write the words for one of them, we just copy every single time. So this is going to be the percent including the tip. Which we're going to have to do a little bit of work to get. Well, what percent of the price is the actual cost of the dinner.
Say that again?
So when you pay just what they charged for the food, that's 100% of what they charged for the food, right? So you always have to pay 100% of your bill, no matter what. And then we're going to add a tip on, which is 16%. So what percentage do I have to pay in total?
160.
Yeah, I have to pay 116% of my original price, right? Because you always have to pay 100%. And then on top of that, I'm paying an extra 16. So 100%, this is my dinner. And then I also have to pay the tip, so plus 16%, which is 116%. And now my base is the price.
Before tip.
Before tip. Which is what I don't know. So amount equals percent times base. So 145 equals 1.16x. I don't feel like doing long division. Oh, there you go. We're just going to save a little bit of time. We only have 7 minutes. 145 divided by 1.16 is 125. So x equals 125. With these problems, always check that you've gone the right direction. So we've got percent increase and percent decrease, which the difference is going to be right here if you're taking away from the 100% or if you're adding on. So once you get to the end, be like, okay, if I tipped, before the change should be smaller than after the change, right? So make sure your answer is smaller than the final amount they give you. That's a good way to make sure that you put everything in the right place, at least.
So by dividing, all you did was 145 divided by 116, and then just make sure to move the decimal back.
Yeah.
Okay.
I just punched in my calculator so we
Yeah, okay.
could spend 5 minutes on another problem instead.
Yeah.
Other questions? On all of these application problems, guys, I think that the biggest mistake people make is trying to memorize like one specific type of problem instead of just working with what you're given. So we have sort of an overall process, and if you take the information they give you and you label it really, really well, then you won't make mistakes with interpreting the problem, and then you can turn it into an equation. Don't try to memorize what this one looks like and what that one looks like and what this one looks like, because it's really impossible for anybody to memorize all the different situations. You just want to kind of roll with what they give you. Let's do one more. We're going to do 14. Which tells me that undergraduate enrollment at a local college or university is 12,000 this year after a 25% decrease from last year. Anybody know what university that is?
Yeah,
Whatever.
Yes. Everybody wants to come here. And we want to know how many were enrolled last year. Now, one thing that's nice when time is involved is that your base is always the earlier time, right? Time does not move backwards. So before is always the earlier date. So we've got amount, percent, and base. Okay, what are we given? We're given that 12,000, right? What is that 12,000?
Current year.
Yes, that is the enrollment after the decrease, right? After starts with A, and so does amount. So, enrollment after the change. Before starts with B, so my base is the enrollment before the change. And that's what I don't know. I do know this year's. What does my percent represent?
Decrease from last year.
So it'd be 75%. Yep.
The 75% I like, but the decrease is 25%, right?
Right, over 100%.
So, but what does my percent actually represent? Does it represent the decrease?
Oh, from last year, so
It represents the percent that I'm left with after the change. Again, what is in parentheses next to amount? Pick it up and put it on the next line. Like, just copy. You can even not even think about it. Okay, so last year we started with 100% of what we started with. You guys agree? And then what was the change? What did we do with that?
Subtract 25.
Yeah, we decreased it by 25%. Which means after the change, I've got 75% of what I started with. So 12,000 is 0.75 times x. And we'll divide both sides by 0.75. Here's my calculator. This one's actually not that bad. I just don't want to spend a bunch of time doing long division. 16,000. So last year's enrollment was 16,000. Okay, just about time to go. Tomorrow you have same thing you always have. So 2.5 through 2.6 online, and then I have a 2.5, 2.6 worksheet. If I could give you one piece of advice for these problems, it is that this is the most important part of the problem. So at some point,